We are looking at our last topic today, which is statistical hypothesis testing. And we're going to start by looking at some basics. And you want to understand this because there's an exam question on this already. So if you don't understand, you ask. There are some tables we shall be using in the process. The Z cumulative table, the Z standard table, as well as, okay, so the standard table, there are two of them. One is either using the one which has a maximum value of 5 or 0.49999, and the other one which has a maximum value of 1. Okay, so I've given them all to you, so start getting them ready. Now, when you go into point estimations, we didn't really do point estimation, but point estimation is where you just execute a point of a statistical parameter. You get a single potential value representing an estimate of the population parameter. Whereas confidence will look at the gap or the interval of that particular parameter you were looking for. And confidence interval is said to be better because it gives you a range that is likely to contain the true parameter of interest. Of course, with a certain level of probability of occurrence. So point estimation and confidence interval are two separate things. Now, if you are going to use confidence interval, I added here that with a certain level of probability. And that is what leads us to hypothesis testing. Hypothesis testing, unlike these ones, it gives you a formal step-by-step procedure to decide between the competing claims or hypotheses about that true parameter value. So what is a hypothesis? It is a claim about a population characteristic, a claim about a population parameter, a claim about the form of population distribution. It's an assertion. It is a conjecture. And you have to subject the hypothesis to statistical rigor until you can say or reject or accept the hypothesis. Now, watch the way I've defined the hypothesis. Take note because I'm going to do you some testing between to strengthen your understanding of hypothesis. So let's take an example to make this definition solid. Let's assume that we have a letter P representing the hypothesis, the probability or the proportion of students studying engineering in the University of Ghana. If the P represents the percentage of students studying engineering, we can hypothesize that P is greater or equal to 60%. In other words, the percentage of students studying engineering is 60%. Now, if we let X represent the height, so that's an example. Another example, if we let X represent the height of the student in the class. Now, watch the word student, even though I didn't use the word average, it's still dealing with the average height of student in the class. Then we can hypothesize that X is normally distributed with a mean of 170 and a standard deviation of 5, which means that we are assuming that the X is normally distributed and it has a mu, and then it also has a standard deviation. All of these help or lead us into hypothesis testing. They all eventually lead us to hypothesis testing. Now, you need to know the null hypothesis and the alternative hypothesis. Who can tell me quickly what is the difference? What is the difference between the null and the alternative?
Doc, the null hypothesis is what is the assumption, what is assumed to be the norm or the truth, the truth, and the alternative is the otherwise.
Give me an example.
So, for example, the exchange rate, you can assume that okay, the exchange rate is, let's say, $1 is, let's say, 12 cedis. So that is the assumption but when we sample and we test, we realize that it is not the case. So that's the alternative.
So what's the null and what is the alternative here?
So the null is the assumption that we make that the exchange rate is 12 cedis to the dollar.
And the alternative?
The alternative is we find that it is not the case. Either it is more, it is less.
Okay. So using the example of X that I've shown above here, what is the null and what is the alternative?
Here, the null is
we don't have, there's no way you can tell because we don't have a parameter.
Yes.
You don't have a population parameter to signal this. So that is not really a hypothesis until you have given a number. Guys, you should know this because there's something about this that is not usually taught at the undergraduate and master's level. So let me just pause this and show you something. It's like something I wanted to show is not yet shown. Who has another example of the null and alternative? Any other example of the null and alternative apart from this? I was trying to. Yes. Who can give me another example of the null and the alternative? This time with numerical values. You remember when I asked you earlier whether your environment you are in is enough to tell you whether you can focus or concentrate on it. All right. Let me take you back here. So for each of the following statements that you're about to see here, why is this thing again? For each of the following assertions here, tell me whether it is a legitimate statistical hypothesis or it is not a legitimate statistical hypothesis. So everybody is going to pick one and then you tell me. If it is a legitimate hypothesis, you tell me yes, it is, or no, it is not, and why you say so. I know that if you are not able to do the first one, you should be able to do the other ones. But let's see who can. So the first one is open, but the other ones is going to be shared among you all. So who can tell me the first one? Okay, H, okay, sigma is greater than 100. Is it a legitimate hypothesis or it is not, and why? Is it a legitimate hypothesis or not? So let me pick on each one of you. Jerry, let's start with him.
Doc, it is not.
Okay. I'll come to the explanation, don't worry. Albert. Ben Susan. Ben Susan.
I'm going to go with Jerry here. I'm still thinking.
All right.
On the
Coffee.
reason. Yes, Doc, can you hear me?
Yeah,
Yes.
Doc.
Hello, I said it's not. I'm good.
I don't need your explanation yet.
Jerry,
Coffee, go ahead.
Doc, it is not. It is not.
All
I
right.
will say it is not.
Emily.
Doc, it's not.
All right. Now, you all said it's not. And because you're all wrong, there's no need to let you justify. I wanted to see, why is this a hypothesis? Now, it is not, and I told you that first one is a bonus to all of you because I'm showing. It is a hypothesis. And the reason why it is a hypothesis is because that sigma represents what? Who knows what that sigma means? What is that? What is that sigma? Emily?
Doc, the standard deviation.
Not exactly. Be clear, be specific. What is that sigma?
It's a mean standard deviation.
Is that what?
Mean standard deviation.
What is that word? What was that?
Average standard deviation.
What is average standard deviation? Why do you have a standard deviation that is not average standard deviation? What kind of standard, Jerry?
The population standard deviation.
What is the word? It is the population standard deviation, which means it is not what? It is not what standard deviation?
Sample standard deviation.
Sample standard deviation.
Now, let me take you back and show you what I define a hypothesis so that I told you to take it well. I define a hypothesis as a statement or a claim about a population characteristic or a population distribution. So the focus also not
Population.
the population and not on the what?
Sample.
So as long as you are making a statement about a population, it is what?
Legitimate.
It's a legitimate
Hypothesis.
what? Legitimate hypothesis. Now let's start. Now that you get a picture here, let's go to the real deal. Everybody's going to take one. So I'm starting again with you, Jerry.
No, it is not.
Why?
It is not. Because we have just...
what is not? You mentioned the thing before you talk is not. What is it is not?
It is not a legitimate statistical hypothesis.
What is not, La?
The mean is not a legitimate...
Which one are you answering? Mention the thing you're answering.
B.
Mention what the B says.
B says that H said that mean of X equals 45.
Mm-hmm.
And I'm saying it is not a legitimate hypothesis.
Mm-hmm.
Because I just understood that a hypothesis talks about an assertion of a population, mean population. But this one is talking about a sample mean. So it cannot be a hypothesis.
Very good. You got it. Let's go to Albert Bensusan. Okay, Albert, I'll put you last because you just came in going up and down. I'll put you last. So let's go to Albert Kofi.
Yes.
The C.
Doc, so it is not because here the S, that is the C, the S represents a sample parameter. And so it's not a legitimate
What parameter?
hypothesis. The S.
Yeah, what parameter is that?
It's a sample. It's a sample. It's a sample.
It's a sample. It's a sample. It's a sample. You have to eat. Oh. What is that? It's not, it's a sample, it's a sample, it's a sample. No, it's not that. What is that?
It's a sample estimate.
No, what sample estimate? What sample is that? Somebody should help him. Who can help him? What is that? None of you knows. None of you knows what this S stands for. Jerry.
So the sample standard deviation.
That is the word. That parameter in question is the sample standard deviation. Guys, you're all going to do some serious mathematical work in your PhD, and it's important that certain things, you know them quickly. Albert, continue now.
Yeah, Doc, because it's not talking about the population standard deviation, and it's talking about the sample standard deviation, then the hypothesis is not an estimate.
Very good. Let's go to the next. Emily.
Okay, so Doc, the D is stating that the standard deviation for the population divided by itself is less than 1. Okay, so since it's dealing with the population, I would say it's a hypothesis.
It's a legitimate hypothesis. Okay.
It's a legitimate hypothesis.
Let's go to the next one. Albert Bensusan.
Doc,
Go ahead.
I believe this will also not be legitimate because it's representing sample means. Two sample means.
All right.
So
okay.
the hypothesis, and from what you
So
said,
that's it. So you guys at least now understand.
Since this is for sample, it will not be legitimate.
It looks like when I'm talking, Albert cannot hear me. Because he keeps talking.
I can hear you. Can you hear me?
Yeah, but it looks like you keep talking, or it takes a longer time for you to hear us. Anyway.
Yeah,
so
I think there's a
move
lag.
on.
Let me try dropping off and coming back again.
Let's move on. We have a lot to do today. So let's try to understand a hypothesis. A hypothesis testing is a technique, a procedure for deciding between the null and the alternative based on the sample information. There are 4 steps in undertaking hypothesis. This is not here. I just want you to know on top of your head. The first step in doing a hypothesis is to formulate the null and the alternative. The second step is to calculate the test statistic and the critical value, and then calculate the p-value and the alpha, or determine the alpha and the p-value. And the last one is to conclude, decide and conclude statistically and practically. So these are the steps in hypothesis testing. Okay, now let's assume that you have this X, which is normally distributed with a population mean of mu and a standard deviation of 10. On the basis of this, you can test the following. You can test the null hypothesis where mu is 50 against the alternative where it's not 50. This is known as a two-tailed test. You can tell me why it's a two-tailed test. Why is this a two-tailed test? And the two-tailed test is based on which of the two hypotheses? Is it the null or the alternative? Now, normally, I know you know some answers, but when the answers don't come, I know that you are not paying attention, normally. But when the answers, the easiest answers, when they don't come early, I know you are not paying attention. When they don't come, then I know it's hard. When it is hard, I know it's hard. But when you are not paying attention to it, I also know. So make no mistake. The fact that you are not showing your video doesn't mean that I don't know that, there are some easy things that you should, if you are paying attention, you should be able to answer. So how do you define whether or not it's a two-tailed test? It's based on what?
Dog is based on the null hypothesis.
What makes you say that?
Yeah, because I mean the test will decide whether it is true or it is not true. So it's more like a binary thing, whether it is true or it is not true, or whether it is the case or it is not the case.
So why that should rather be based on the alternative? Because the alternative gives you two options of whether it is above 50 or is below 50.
Yeah, but then we conclude with it now. We decide whether we should accept the null or we should reject the null. So I think it's because we are either we are going to accept or we are going to reject. That's how come it is two-tailed.
You are going to accept based on whether it is above or below the 50.
Yes.
It's not based on itself. You accept or reject based on whether it is above or below the 50.
Yes.
So the alternative is what is used to determine, because the alternative has got two directions. That's why it's called two-tailed. The alternative can have one direction, which is a one-tail, or it can have a two-direction, which is a two-tail. So use alternative to determine the tail of the test. Okay. Another thing you should take note of is type 1 and type 2 error. You should know this because we're going to answer a lot of questions on them. A type 1, and most of these things in your PhD, when you bring them, they know that you understand because you understood them from here. Because anytime you are developing a model, you have to test whether the model is good. And one way you can test is using simulation. And simulation will use p-values, type 1, type 2 errors, and things like that. A new model which has never been done before, you can collect a simulated data to test whether your model matches reality. The reality is that you've not collected a real data, but you can generate a simulated data and then test whether the 10 matches simulated data, as long as that data has a distribution which follows the distribution you are interested in. If it is efficiency scores and it is, non-parametrically distributed, then you will know the model you have to choose. If it's a normal count, count variables, once you know the distribution, you can test. So simulated data doesn't matter. As long as it follows the distribution required, that data can. So you should understand type 1, type 2 error. You should understand the error. You should understand the p-value. You should understand the alpha. You should understand all of these things. So what is a type 1 error? It's rejecting a null hypothesis when it was true. It's wrongly rejecting a null hypothesis that is true. In other words, rejecting a true null hypothesis. A type 2 error is actually accepting a wrong null hypothesis or a false null hypothesis. So the null hypothesis is false, but you accept it. That's type 2. And we use the symbol alpha and beta to denote. So alpha is the probability of rejecting a type 1 error. Beta is the probability of rejecting a type 2 error. You can see that also here. Okay. So the probability of rejecting a type 1 error when it is true, that is a given that it is H0. And then the probability of accepting a null hypothesis when it is false, that is a type 2 error. That's a beta. Keep those in mind. Write them down if possible. Now, it can be shown that both the type 1 and 2 errors can not be simultaneously minimized. Usually we fix one of the errors, say type 1 error, and choose a test that minimizes the type 2 error. In practical sense, type 1 error can be 5%, or type 1 error can be 1%. The best is type 1 error being 0.1%. There are basically three major ones, sometimes four. 4 is when you include 10%. That is actually 0.1%, 1%, 5%, and 10%. Okay. Now, another thing you should take note is the level of significance. Okay, the alpha is also called the level of significance. The alpha, suppose you are doing a research, alpha is the error you are expected to make. Write it down. Alpha is the error that you are expected to make in the research. So there is a modicum of error you are allowed to absorb. And then you later learn that the p-value is the error you actually make. So the alpha, which is the probability of committing a type 1 error, is actually the level of significance of the test. And whenever you have a test statistic like t, it's a standardized function of x, which is from x1 to xn. And this are the actual numbers. The actual numbers are the random numbers of which you normally will find the what? The average. And then finding the average, you juxtapose the average against the existing true average. And then you have to create a critical value. Okay. And then set up a rejection region. So as an example, I'm not going to go through much details. You should know these things. Okay. The section on the edge in a normally distributed curve, these edges here are the rejection region. Everything in between these two, okay, this blue space is the acceptance region. And the gap that is here is what is known as a critical value. The critical values are here. The center is 0 for a z, and it is actually the mean, mu, for the random variable itself. So as you move to the right, you are in the positive domain. In the random variable sense, as you move to the right, you are actually moving to the right side of the mean. When you are moving to the left, you are moving to the left side of the mean. The mean is always positive. Sorry, the random variables are always positive. Okay, so you moving to the left means that you are still moving to the positive value of the random value. But when you are dealing with z, so this line can represent z and at the same time can represent x. But then the center of the x is a mu, and the center of the z is 0, which means to the right of the z is positive, to the left of the z is negative. But everything of the x is positive. If you don't understand, ask. Okay. Now, a test with a significant level of 0.5% means that when the test is repeated several times, only 5% of the time, the type 1 error may occur, which is good. Okay. So you get that error happening only 5% of the time, if it is within that 5%. But 1 minus the b, which is the probability of rejecting a true null when it is false, is called the power of the test. So when the type 1 error is falling, then the type 2 error will be rising. That's a very key important point, because the other one, the 1 minus the b, that is the 1 minus the type 1 error, is the power of the test. Okay. And you have to allow a certain percentage. So the largest tolerable value is decided based on the problem under the consideration. Okay. So these are the basic definitions that you should note before we come to the real deal. If you don't understand, you may ask. So let's take a typical example, which is like an example. It's not your usual type of exam questions. Okay, so the key is to understand the terrain. 2 companies have applied to provide cable TV in Accra. They are providing the services. One might be DSTV, one might be GoTV or something. Now, if we let P represent the proportion of all the potential subscribers who favor the first company over the second company. So the percentage of the people who like company 1 over company 2 is P. Then we can now formulate a hypothesis in the name of P because P is supposed to be equal to 50%. Okay. P means probability, so we want to just split it. Now you have to test the probability that the percentage is 50% versus the alternative that is not 50%, based on a random sample of 25 individual people. Let X denote the number in the sample who favor company 1, which means that the number of sample who favor company 2 will be what? Have it.
50%.
1 minus X.
Yeah, that is only if you have defined X as, if you have defined that the number in the sample who favor company 1 plus those who favor company 2 is 1. But we haven't said that. Wow. Albert Kofi.
Hello, Doc.
What is happening in your background?
Oh, there was a call coming through. I've connected on my phone.
So put it on vibration, silent. That is a very technical way since you are in a boardroom.
Sorry.
Because the next thing you're going to say is sorry, which doesn't help anybody. All right, because the thing is being recorded, guys, so pay attention. All right, so which of the following rejection region is most appropriate and why? Okay, so these are the rejection region. Which one is the most appropriate and why? The first rejection region is X is less than 7, union X is greater than 18. The second is X is less than 8. The third is X is greater than 17. Question is, if you are very, very smart, you would have detected the answer quickly. But let's still go through it. Yes, Emily, how will you answer this?
Okay, Doc, I'll say the R1 is the most appropriate because based on the test, you can see it's two-tailed. So it will have a less than and then a greater than.
That's a perfect answer. That is a clear, easy answer for that. Okay, she's just nailed the point right there. Who doesn't understand? So these are some of the questions you should take note. We are building on this same question. If you look at a hypothesis, it is a two-sided hypothesis. It's a two-tailed. And because the alternative is saying that P is not equal to 0.5. Please, just a second, let me. All right, so Emily, the answer that you gave is correct. We go to the next one. The first answer is that the probability, as you can see, is 50%, not equal to the alternative, which means that you have extremely low values of X, which will be below 50% probability, or high values, which is above. The next part of the question is describe type 1 and type 2 errors in this problem. Describe the type 1 and type 2 errors in this problem. How will you describe the type 1 and the type 2 errors in this problem?
The tablets also.
How will you do that? Okay, let's go through that together. So the first thing is that the null hypothesis is that P is equal to 50%. The alternative is that it's not 50%. We know from here that the sample size was 25. The test statistic that could be used to analyze this, if you check carefully, if we are to use a test statistic, given the fact that the sample size is 25. Ideally, we would have used the T, but 25 is big enough. Okay, it's big enough so we can move and go to Z. Besides, remember that you can approximate T to Z. Okay, so on the basis of that, we can make a decision that we want to use the Z. Okay, but when you approximate, you can approximate B, or what do you call it? You can approximate T to Z. You can approximate Poisson to Z. You can approximate binomial to Z. But if you look at the hypothesis very carefully, because we have been given a proportion above and below 50%, we can say that the fact that you have the choice, if you can see the company, people have the choice of favoring company 1 or favoring company 2. And that favoring will lead to a binomial distribution. So we can detect that this can be estimated as a binomial distribution where the sample size is 25 and the P is 0.5 and the 1 minus P is also 0.5. Okay, that's a second. All right. So since N is moderately large, we are going to use a normal approximation of binomial distribution. Okay. So in a normal approximation of binomial distribution, or in a binomial distribution is distributed with a mean of N times P. If you could remember, if you can remember back the mean, okay, of a binomial distribution is NP. N is a sample size, P is a probability of success. N is 25, P is that, so you have 12.5 as a mean. So it means that I can now use this graph, going back to the point even Emily answered, and say that the middle here is 2.5. Okay. Now, the next thing is that we can find the standard deviation, because the variance, you don't only find the mean, you also find the variance or the standard deviation. Either way, we want to find the variance. The variance is given by the square root of NP 1 minus P. Okay, NP 1 minus P. And NP is actually the sample size multiplied by 0.5 multiplied by 1 minus P, which is also 0.5. And you take the square root of that 6.25 multiplication, and that gives you 2.5. So it means that the standard deviation is going to be 2.5. Okay. So you have the mean, and then you have the standard deviation. And then you were told the original question. Okay. So now you see that if we are to distribute it normally, X can be distributed normally with a mean of 12.5 and a standard deviation of 2.5, or a variance of 2.5 squared. Okay. We need to have that two-sided region. Okay. Emily spoke about it. We spoke about it. So we're able to detect that if you use these two directions, it's better because it's looking for X is less than or equal to 7. Union X is greater than 18. So here I can detect 7 here. Okay. I can detect 7 here. And I can detect 18 there. So if I have 7 and I have 18, okay, the rejection region makes sense, because once you have that, you see that the acceptance region will be exactly here, which falls between. So this two-tailing actually matches what the hypothesis is saying in this case. The distance from the 7 to the mean is 5.5, and you can see that 5.5 is actually in the rejection region. Okay. The distance from the mean to the 18 is going to be another 5.5, which, if it is added to the 18, you to also be in the rejection region. Okay, and this is the exact graph that I've indicated. So you can see clearly that the R1 matches exactly the rejection region that is being expected. If you take the other two, check it carefully. Okay, the other two are not symmetric. For example, this one will give you only one tail, and then the other one will also give you only one tail. Both of them are wrong hypothesis given the information that you have here. Now, the second point is describe the type 1 and the type 2 errors in this problem. Describe the type 1 and the type 2 errors. How do you describe it? First thing, what is a type 1 error? False alarm. Rejecting the true null hypothesis. The null hypothesis is true. Okay. The null hypothesis is not it's true, but you reject it. Okay. So I've given an explanation of type 1 error here, which happens when you decide, in the case of the companies, one of the two companies favored over the other, when in fact there's no favoritism. Okay. So when you favor one of the companies over the other, but then they are all indifferent, then you've committed a type 1 error. Because remember, the type 1 error is actually rejecting that true null hypothesis. And what is the true null hypothesis? The true null hypothesis is the fact that people favor one company over the other. Okay. So when you decide, and that is the truth, but when you decide that, oh, they don't do that, okay, then you are committing a type 1 error. So when you mistakenly decide that there is a preference between the two, when actually there is no preference, okay, and when there is no preference, it means that one is better than the other. That's what it means. That is when you committed a type 2 error in this sentence. In this sentence. So when you have a sentence, you should be able to identify where is the type 1 and where is the type 2. Now, type 1 actually is defined as accepting a false null hypothesis. So you have a type 1 error, which is a false alarm. A type 2 error is not. Okay. But that is judging that the 50%, the two companies are indifferent. You are indifferent between the two companies. When in fact, you gotta be indifferent. When you have to favor one over the other, but you say that you don't favor one over the other. Okay. So you fail to dictate that one company is genuinely preferred, even though the real differences, a real difference exists in the population. Even though, there is a particular real difference. So that is how you address a type 1 and a type 2 error. You got to know that addressing a type 1 and a type 2 error practically like this is not a simple joke. You got to master the ingredients of doing that. But first, you got to know what a type 1 error is on top of your head and a type 2 error is on top of your head. The next thing is, what is the probability distribution of the test statistic? Remember, the test statistics is X. We don't know it, but what is this probability distribution, especially when the null is true? And now, after you've dictated it, use it to compute the probability of the type 1 error. In other words, what is the probability of type 1 error? What is the probability of type 1 error? What is the probability of committing a type 1 error?
That would be the alpha.
Alpha. Excellent. So so you are going to find the alpha. Okay. But first, we have a binomial distribution. The sample size is 25. The probability of success is 0.5, which is 50%. And that is a null hypothesis. Okay. So with this information, we can say that if you are to distribute this thing binomially, you're going to have 25 against 5, where 25 here is the sample size, and then 50% is the P, the probability of success. So this is a binomial distribution. You remember that we converted it into, we found the mean, which is NP, and then we found the standard deviation, which is the square root of NP into bracket 1 minus P. We found that. We've already explained what a type 1 error is. A type 1 error happens when the null is true, but we reject it. And what is the true null? The true null says that the people prefer one company over another company. And because they prefer one company over another company, what happens here is that is what you should go for. There must be a preference, but you rejected a preference and you say there's indifference. Now, if you want to compute that type 1 error probability, the alpha, you got to define the rejection region. We got to know, and to get a rejection region, remember the chart, you need to know the critical value. Because, and when I say rejection region, I mean this. You need to find this part here, this shaded part, then that shaded part here. You need to find it. But to know that, you need to know the critical value, the edges. So that is the steps you got to take before you can now know the probability. Okay, so how do you do that? We already know that we can compute the type 1 error. Okay, so we start with that. What is the alpha? This is how we can get the alpha. The probability of committing a type 1 error is the alpha. Now, alpha is found by the probability of x being less than or equal to 7, and then s being greater than or equal to 18. Now, these two values, you can use them you can find their corresponding z values. Do you know that? Do you know that? You can find that. But then the whole thing is binomially distributed. So you got to go and take the binomial formula. And what is the binomial formula? Remember, the whole thing has been binomially distributed here. And now you're going to find a binomial function where x is less than or equal to 7. Now, let me just remind you of the binomial formula. This is the binomial formula. Okay, if you can remember, the binomial, okay, is normally given by blah, 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 blah. But I've just simplified it here. Nk, and then p raised to the power k. But we used to normally use like, that's a probability of success raised to the power k. We used to call it x, if you can remember. Okay, but that's the same x here. And then 1 minus probability of success, which is the probability of failure, raised to the power n minus k. And then you now calculate that binomial formula. Guys, do you remember?
Yes, Doc.
Yes, yeah. Remember.
Who can tell me how the formula really looks like? It's not exactly this, but how it really looks like. This part, how does it normally look like? Because there's usually a factorial in there.
Though I think that's what is in the n and the k. I think you just have to rewrite it as n factorial, n minus k factorial, k factorial, and then the rest follow.
Exactly. You can use x or you can use that. Now, I'm not going to work that. I deliberately ask you so that you can tell me which means that you can do it. If you have forgotten, you can say it, we can help you now. So I'm going to do that for 7. See, but you see, if you're doing it for 7, it's not going to be simple because you're going to do for what value to 7? From what to 7? Because if you look at it, it's not just 7, no. It's not equal to 7. It's less than or equal to 7. So from what value?
0.
0 to 7.
So for each one, you're going to use this value. And you better. There is usually a table you can use. But that table, I like you guys to calculate it yourself. So forget about the table. So this is how you do it. You find for 0, find for 1, find for 2, find for 1, and 3 all the way to 7. And then from 18, this one you do from 18 to what? You do from 18 to what?
No,
Remember the sample?
25.
25. So you have to calculate from 18, blah, blah. Okay. So if you do that, you're going to get this. Now remember, what we are doing is that we are looking for the region. Look at the question. What is the probability distribution of the test statistic when the null is true? Use it to find the probability of the type 1 error. So we need to get a critical value, and then we can sum this. So when you get these numbers, so you got to calculate for this, but you can see that here I've written the formula as from 0 all the way to 7. So you have to do it one by one. From 0 all the way to 7, from 0 all the way to 7, from 0 all the way to 7. And then you calculate that. If you do that, okay, you're going to get 0.2. When you do that for each one of them and sum them, you're going to get 0.02 and another 0.02 in both cases. And when you sum those two 0.02s, that is for the one above 18 and the one below 7, you get 4%. So our alpha now is 4%. Yes, Emily.
Okay, Doc, please, I just want a little clarification on this. The 7 and 18 that we have right now is because the A part was asking us to choose which one was more appropriate. So in case that question is not there, how do we get the 7 and 18? That's the critical point.
Which one was not appropriate?
Is it the A part of the question was asking us, it gave us 1 2-tailed one, and then the other ones were just 1-tailed. So we chose this one. Okay.
Because that was the one that was favored the hypothesis, right?
Yes.
Mm-hmm.
So in case that wasn't there, how would we be able to get that is 7 and 18 that we need to use for this?
You would have been given, or you would have been given one to select in the first place before you proceed with that.
Okay, thank you.
All right. So once you get these values, you now have your alpha. So the question is simple. The alpha you're looking for is at 0.4. So the type 1 probability error is approximately 4%. For the region where x is less than or equal to 7 or x is greater than or equal to 18. That is your probability. Any question? Remember that the question itself asked you to find something before you find the probability. He was asking you to find the test statistic. And the test statistic was the 7 and 18 with their parameters that were dealt with. So it is the 7 and 18 that you got to find, you got to determine first. But of course, it comes from there. Because remember, he didn't tell you that they are that. They say when the null is true. But in the previous question, you were asked that if the null is true, then what is going to be the parameters? And then those parameters were good. Okay, let me just take you back there. Because he's focusing on when the null is true. But look at the first question. Come on. Okay, which of the following rejection region is most appropriate? That word most appropriate is matching when the null is true. Do you know that? That 7 and 18 you selected was matching when the null is true because the one that contains the 2-tail is with the one when the null is true. So it was a follow-up from that. Okay, so let's go to the D part. The D part says that, that one we seem to have, okay, I'll show you. I mean, we just missed that part, but it's okay. So compute the probability of type 2 error for the selected critical region when the P is 4. You see, that question P is 4 is expecting you that you must have gotten the previous one to be P is what? 4. But the thing is that, sorry, not expecting it. I mean, he's giving you a different probability value. Okay, the original probability value was 50%. Now he's giving you 40%. So you just formulate the same thing, but just that you change the 50% to 40%. So before, the critical region was 50%, okay, and you were rejecting that null hypothesis if this x was below 7 and above 18 inclusive. And we saw that acceptance region therefore becomes, watch it, the acceptance region becomes anything after 7, which is 8 and 17. So that becomes acceptance region And then these ones becomes the rejection region. We know that. Now, what is a type 2 error? It's failing to reject the false null. Okay. Now, this is a type 2 error. So if the probability is not equal to 50%, but it's equal to this one, okay, and you fail to reject this, okay, so if this one, if the thing is not equal to 50%, if it's not equal to 50%, then it is 40% here. Okay, if the 40% is true, okay, but you fail to reject the null and take this one. So what does that mean? That is a type 2 error. So we are simply going to do the same thing, but this time we are not finding alpha. We are finding the beta. Okay? By replacing the 40% with the 50%. You're still using the same acceptance region here. And of course, still going by the normal distribution, you find that n is 24. This time, the probability of success is 40%, so the probability of failure will be 60%. Okay, and you substitute that into the equation. But remember, this time we are finding between 8 to 17. Oh. Remember the previous one, we found between 0 to 7 and added it to 18 to 25. But this time we are finding between 8 to 17. Okay, so of course, if I'm giving you this, I will give you one that the gap is smaller. Because 8 to 17 means you got to calculate 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 10. Okay, that is quite a lot. So you find that. So you take the same thing and this time find that same value and add them. Add 8, 9, 10, all the way to 17. And when you do that, you are going to get some. If you use a table, okay, that complex table they spoke about, but the principle is the same. You add all of these probabilities together between 8 and 17, and that is going to give you 0.0845, this one, 0.0845. And that is the probability of committing the type 2 error. Okay, now finally, using the selected region, what would you conclude if 6 of the 25 favored company 1? If 6 of the 25 should favor company 1, what will you do? Now, this is a very simplest answer. Which region do you think that 6 will fall into? Will it fall into the acceptance region or the rejection region? Albert?
Oh, the rejection region.
Exactly. That's the answer. Watch the answer. Watch the question. Okay. What would you conclude if that? So what will be your conclusion? If 6 of the 25 favored company 1, you reject what? Because if that will fall within the rejection region, you reject what? The null hypothesis. Okay, that's what you do. You reject the null hypothesis. Okay, in favor of the alternative. Very, very simple thing, but you get when you draw some of these things, it gives you a better perspective. So that means that fewer people prefer company 1 than company 2. Any question? I want this to pause and sink in. Let's continue and look at the next question. Again, this time you are getting a bit deeper. Each one will be teaching you whilst preparing you. A new braking system designed for BMW cars has been proposed. Now watch the sentence. A braking system. Now let me ask you, do you want something to brake faster or to brake slowly when you're driving?
Faster.
Okay. Emily, you haven't been driving, so the answer you give, let me ask the experienced people. The experienced people, when you are driving, you want the brake to brake faster or to brake slowly?
Look, both of them are not. Both of them can be risky because if it breaks faster.
I'm understanding my question. My question is that braking system. Who is talking behind the scenes? Braking system, has it been designed To brake faster or to brake slowly? That's what I'm
But
doing.
to brake faster so that you don't hit someone.
Brake faster so you don't hit someone. Okay, maybe I need to put how many miles per hour flying, then you can understand. Now, when you are even standing in the traffic and you remove your leg from the acceleration, like you're on a brake and you press the brake again, what happens? Even if your leg is on the brake and you remove your leg from the brake and you press the brake again, what happens?
The car jerks forward.
Sorry?
The car will jerk forward.
Yep. And if there are children in and who don't have seatbelt, what happens?
Or they'll be thrown forward. They could hit.
You can knock them, yeah.
So now keep that mindset. And when you are now speeding and you want to brake, and you press the brake like that, what happens?
Oh, you throw the people out, so you typically will brake gently.
A new braking system has been designed for BMW cars. And the company wants to implement this new design only if the data provides sufficient evidence that the true braking distance at 40 miles an hour is below the current mean of 120 feet. So the thing is that there is an existing braking time. And the existing one is how many? Is 120. That's the existing one. And for the new braking system, which has been developed for BMW cars, for it to be a good one, must it be below the current one or above the current one?
Be below it.
Okay, so the first thing is that define the parameters of interest and state the hypothesis. So what do you think is the parameter of interest? And when I say parameter, I'm sure you understand what I mean by parameter. What is the parameter of interest? Albert.
The braking distance.
Yeah, what is that parameter of interest?
The braking distance, the distance in feet.
The braking distance. Okay. Guys, do you understand? So the parameter, and this braking distance, what is the parameter name? What parameter are we talking about here? What statistical parameter?
The mean.
The mean, that's what I mean. A parameter is either the mean, the median, the mode, those are the things. Okay, the standard deviation, the variance, these are the things. All right. But they are all, if you want to use them for hypothesis, they must be the population. Okay. So if we are to define the parameter of interest, it's the mean. So the mean represents what? The mean represents the true mean braking distance. Okay, the true mean braking distance. So if we are not supposed to formulate a hypothesis, how will you formulate a hypothesis? What would be the null hypothesis? Oh, please note that the null hypothesis always carries some level of equality in it. So how will you write the null hypothesis? Of course, using the mean. How do you write the null hypothesis? And how do you write alternative hypothesis? Remember, the null hypothesis always carries some level of equality in it. So the word below. Yeah, go ahead.
It will be mu less than or equal to 120. And then alternative will be mu greater than 120.
Very good. So guys, this is the now. Now, what does the first one mean in English in terms of the braking system? What does that mean? Albert.
Look, it means that an average BMW at 40 miles per hour brakes at 120 feet, breaks in a distance of 120 feet or below.
The null or the alternative?
I'm talking about the null.
Did you use the word below? Did I write? Oh, I made a big mistake. I can't believe that I made a big mistake. Can't be that. And the word below. Only what were you guys thinking? Look at the word below here.
Yeah.
That word below, it can't be. So the word below, the below must be here, and the null must be this. The alternative must be that. Okay, which means that it's opposite. What's the opposite of less than? What's the opposite of below?
Greater than or equal to.
Greater than or equal to. So, to be greater or equal to, which is above and equal to. Okay.
Yeah.
So this is how the null and alternative hypothesis have to be represented. I don't know who gave it to you, the one I wrote before. But again, it shows that some of you are not paying attention. Okay, so what does the first one mean? In simple language, in terms of the new braking system, the first one means that the new braking system is what?
It's braking in
Is it good
a
or not
distance
good?
greater than or equal. Not good.
It's not good. Okay. And then the alternative means what?
That it's good, that it's doing its preferred job.
The alternative means the new
It's
system
good,
is
it's
better.
braking, yeah.
It's better. And better here means that it's what? It has a shorter braking distance.
Exactly.
That's what it means. Okay. So the first one has a longer braking distance. Or the alternative is that the current one has a shorter braking distance. Now, so what it means is that the null is saying that the first one is not that effective. And this one is saying that the thing is, because for it to be effective, it has to be below the current braking distance. So that's how you define it. If you, yes, Albert.
Doc, in the definition, do you need to put the 40 miles per hour there?
No. The 40 miles has nothing to do. The 40 miles is not the mean. The mean is a 120.
Yeah. Okay.
The 40 miles is just the rate of speed.
Acceleration. Okay.
Yeah. All right. So now the next question says we want to choose. Okay, let's go to the question. The B part. Suppose the braking distance for the new system is normally distributed. Okay, so now you know that it's normally distributed, not binomially distributed. Okay, it's normally distributed with a standard deviation of 10. Let X bar represent the sample mean of 36 observations. Which of the following 3 rejection region is appropriate? So first, if it is normally distributed, then we can convert the standard random variable to a z variable, isn't it? That's what it means. And z variable means that you should have z equals to x bar minus the mean over s divided by the square root of 10. That's what it means. What is x bar?
That's the sample mean.
Yeah, you have to take one of the ones that has been given to you. So you have to work for the 124 and work for this one and work for that one and work for that one. Remember, we are looking at, first of all, you need to find the standard error anyway. The standard error is the denominator here, the s over the square root of n. What is that value? You need to find that. So that is, that is 10 divided by the square root of 36. Is that it? Something like that, right? 10 divided by the square root of 36. So let's look at that together.
That's 1.637.
Okay. We already know that the whole thing is a one tail, as you can see. Okay, it's one directional. So we have this. Let's find the standard error. 1.6 is what?
7.
Very good. So that gives you the standard error. Now you can put it back into the equation and check for each one of them. Now, the best thing you can do is to draw. Okay, is to draw, because when you draw, you're going to have something like this. The mean is 120, so you put 120 here. Okay, and then you take, see this one, the first option. If we draw, 124 is going to be to the right of that. Actually, it's not asked you to find. 124 is going to be to the right. Okay. So let me just go back here. We want to choose. What was the question? Let me just go back. It says that which of the following three rejection is appropriate? All right. So you want to choose a rejection region, okay, for the testing process. And so you find this one, and then you check the rejection region. You see that 124 is above the 120. 115 is below the 120. 125 and 120, 114. If you check 125 and 114, one is above, one is below. Okay. And so if we are to find the rejection region, so we draw each one of this, we find the rejection region. You see that the rejection region, the 115, which was the third one that was given, the second one that was given, will be exactly below. I want to define the parameters of interest for you. And you will notice that the 115 is below. Because watch the sentence. We are rejecting only when the sample mean is below the 120. If you remember the alternative, for the current braking system to be wonderful, that current braking system has to be below 120. So when you look at these numbers here, the question becomes which one of them is below 120? Now, this one would have been good, but the fact that he has brought the 125 on top of it makes this last one bad. Are you guys with me?
Yes, Doc. We are with you.
Yes,
So the
Doc.
one that is below 120 is the 115, and that's the only one that's below the 120. I said if you draw is better, but you can just look at it with your mind and you don't have to even draw. So the next one, what is the significance level for the appropriate region of part B? So we've selected the appropriate region. Appropriate region is what? 115.52. That's the one. Okay. So now knowing that we can find our Z value. So Z value will be equal to the mean, which is what? X bar. The X bar here is 115.52 minus the mean. What is the mean? 120.
20.
Divided by the standard error, which was what? Remember, we found the standard error already.
Yes, Doc.
So that will give you what Z value. If it is negative, to indicate it. If it's positive, indicate it. What will be the Z value?
Negative 2.687.
Correct. Always to two decimal places.
Okay, so negative 2.69.
Okay, good. So that's a Z value. Now, remember the question we are looking at here. Let me just take you back to the question. It says that what is the significance level? So we want the significance level for this appropriate region. Okay. We want the significance level for this appropriate region. How would you change the region to obtain a test with rather a significance level of 0? We'll come back to that. So what is it going to be? So to find this, you've got to go and read it from the Z table. Okay. So let's go to the Z table. You can take one of the two Z tables. Let me show you one of them. I sent it to you guys. And in an exam situation, you have all these two Z tables. Oh. Hold on, let me just open it first before I show you. Okay, there you go. So you have this Z table. This is a cumulative one, but that's not what you're going to use. Okay, you're going to use this one. No, this is rather the cumulative. So you're going to use this one. I said, and there are two ways you can do it. You can either use this one. You see, this one goes from 0.5, which is the lowest level, all the way up to 1. Okay, you can use that, or you can use the Word document one I sent you. So check either one of them. Either one of them is going to give you the same thing. In fact, let me show you the Word document. This is also the Word document one. So when you look at it, we are going to look for 2.6 under 9, isn't it? 2.6 under 9. 2.6 under 9. So where's 2.6? That's 2.6 under 9. Under 9 is here. So what do you get? The value you get is 0.4964. 0.4964. Now remember what we were doing. Let me just remind you. When we drew the thing, we had the mean here to be 120. The corresponding Z is 0. We found a Z value of 2.69 negative. So that is here. A negative 2.6. We had our critical value. What's our critical value? We had no, this one is just, the question was asking you to find the probability. Okay, let me just go back here. It says that, okay, you don't see, let me show you. It says, what is the significance level? So you just want the significance level. Okay, so the significance level, how do you find the significance level? We just match these two numbers and we got a significance level to be, we got it to be this. Oh, we got it to be that. Okay, with 2.6 matching that. Okay, so ideally it would have been 49.64%, but that is not the case because we are looking at below. Okay, so when you draw this thing, we had 120 here, and then we saw that we are dealing with what? 115. Okay, so if you have to go for 115, 115 is somewhere here, right? So that is 115 point. It was 115 point what? 0.52, I think. Okay. And we are looking at below. So below means that we are looking at this section. Okay, it's for the rejection region. That's it. Okay, and to get that value, we need to find this space. This space is the one we just found down here, which is a 0.4964. So if we want this corner here, what do we do with that number? If we want this corner here, what do we do? Albert.
Yeah, we subtract it from 0.5.
Exactly. And when you subtract it from 0.5, what do you get? .5 minus 0.4964. Participate though.
Oh, sorry, 0.0036.
Good. Now, if we were to use the other table, let me take you back to this other table. If you were to use this other table, and you have to look for 2.6 under 9, watch it. This is what you're going to get. 2.6 under 9. Okay. It's still going to give you that under 9 is going to give you the last one. You get 0.9964. But this one, you subtract it from what?
Doc 1.
And what do you get?
0.0036.
The same thing. Okay.
Yes.
So either you use any of these, you can still get your answer. Okay, let's go back. Let's go back to the question. So the question says, what is the significance level? We just found our significance level. So when you go through it, everything we did is here. Take the Z curve, find this. Now find the left side probability. You either do 0.5 minus the point blah, 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 or the 1 minus that, and you get the same thing. So this is appropriate significance level for that question. The question says, what is the significance level? And the significance level is what you just want. The next part says, how would that significance level change? How would you change the region to rather get a test with a significant alpha of 0.1%? This is a beautiful question. In other words, how are you going to get a test of that value if you change? So this is an interesting question. Okay. It says that the same way, remember the formula that we got? This is a formula. The formula is Z is equal to X bar minus mu over S raised to the power divided by the square root of N. Okay. We were able to get this Z and use the Z to get the probability. Always remember that you get X, you use the X to find the Z, then use the Z to get the probability. Pay attention here. You can also do it backwards. Instead of doing this front, you rather do it backwards. And how do you do? In other words, how do you find X? That's what the question is asking you now. How do you now find it? How do you move backward? Suppose I now give you the probability here, which is P. Okay. How will you now tell me the region? What would be the X value? That's actually what it's asking. What is the X value? If I give you the probability, what is the probability? 0.001. Okay. How many percent is that? It's almost 0.1%. So what do you do now with this probability? You go and dump it into the Z table and look for the numbers closest to that. But watch it. This sentence requires you to use a cumulative probability, okay, approach, because you can't use the ones we are dealing with now. You have to use a cumulative probability because the sample size was 36, don't forget. So that's Z. So let's go to the cumulative probability. So not this probability, but the cumulative probability. Because this one, if you're looking for 0.001, you will not get it. You will not get it. Well, technically you will. You can get it, but it's not enough. I'll give you ways you could have get it, but it's not enough. So whatever you had, that's 0.001, subtract it from 1. What do you get? It's 0.1%. 0.1% is the lowest you can ever get, the lowest probability.
Yeah. Okay, you get 0.999.
Exactly, which would have brought you here to this one. But this table is not enough. What I'm saying is that, I mean, it's not the full table, because the full table normally will go all the way to, sorry, this is cool. This is cool. Okay, so you dump that one, that 0.001 into here. But before you can dump it, you need to subtract it from 1. And when you dump it, it matches this one here. So if you have to read the corresponding Z, what does it become?
3.09.
3.09. Isn't it?
Yes.
If you want the 0.11 table directly, which is we call the cumulative table, this is the one. This is the one. So you come and look for what do you call it? 0.0001. Oh, do you get it? You see, that one is here. If you check it, that one is here.
Yeah.
Isn't it? Mm-hmm. Okay, 0.0001. 0.001. Isn't it? And when you match the corresponding Z, what do you get? The same thing. It's symmetric. You get negative 3.09. But let me ask you, which one will you take, the negative or the positive?
Of the negative.
Exactly. Why?
Because of where it's shaded. So it's on the left-hand side of
Not
the mean.
because of this table. Just go to our own.
Yes, Doc. Our own is like that also.
Okay, what makes it like that? Because our own, the what do you call it? The value we are looking for. Yeah, the value we are looking for is below the 120. In fact, everything we are looking for should be below. And if it is below, it means it's on the left side of the Z. And that is what we've got to use. Okay, good. So now we are going to take this value, okay, and then dump it into our equation. So let's go to our equation. So now we're going to have Z, but we don't have, what do you call it? We have gotten the Z value. So the Z value is negative 3.09 equals to X bar, which is what we are looking for. We don't have it. Minus the mu, which is 120, divided by, is it 1.66? Yes, 1.6667. Okay, so now find the value of X bar. That's what you're looking for. Find the value of X or X bar. The same thing.
114 points.
Exactly. 0.8 something.
Yeah.
That's exactly the answer that we are looking for here. Okay. So let's check it. So you do all these things that we did here. Okay. This was a point. This is what we call here the cutoff, but it's the same thing that I did. Okay, it's finding the X. And you substitute that, you get the value of Z, which is negative, blah, blah, blah. Okay. You can find it on the table just as we did. You substitute it into the equation. We know the value of this. You substitute that, all of this manual thing will lead you to that same 114.85. So what does this mean? Going back to the question, what does this mean? This 114, what does this mean? It means that if you know the probability that there is a 0.1% chance, then the critical value that can help you to get that 0.1% is 114.85. So the new region for this one is going to be 114.85. So you got to understand the steps in hypothesis testing. Let me just tell you, the steps in hypothesis testing still come to play here. Find the null and alternative hypothesis. There have been different ways we've tried to do that. Find the test statistics and the critical value. There have been different ways we get that. In fact, this one that we just found, the one before this was finding the probability. Okay, the p-value. And this one is finding the X if the p-value is known. Okay. Now let's look at the next one. What is the probability that the new design is not implemented? Okay. Say it's actually 115 and the appropriate region from part B is used. Okay. Remember the appropriate region from part B? Let's go back here. This is for part C. Part B, we are using 115.52. Okay. So how do you work that? You're using the appropriate region for part B. Now, from part B, what was the alpha? Let me just remind you quickly. Part B, alpha was 5%. And if you could remember, it was also one-sided. Okay. So if it is one-sided, what would be the critical region? Well, the critical region is the one we just found, 115.52. That was the critical region. In fact, that's another way of saying that what is the benchmark? There's a name for it. The critical test, the Z critical. The Z critical. The critical value. Critical value. So the critical value is this 115.52. Now look at the question. What is the probability that the new design is not? If it is not implemented, what does it mean? The new design is not implemented. When you say it's actually 115, instead of the 115.52, no, it says 115. And then this appropriate region is used. That word is not implemented means that we are looking for the probability of not rejecting a false null hypothesis. Now, guys, what is the probability of not rejecting a false null? That is what type of error is that? The probability of not rejecting a false null hypothesis.
That's a type 2.
It's a type 2 error. Okay.
Yes.
So actually what we're looking for is a type 2 error. And how do you find a type 2 error? Well, we're looking for type 2 error when the 115 in the question here has been given. So we are looking for the probability that X is greater than that of X bar here, this one. We're looking for the probability, that X is greater than this. So, and of course, to do that, you have to juxtapose that against this 115 they've just given you. So you are finding a new Z, basically. You are finding a new Z where this new Z you are finding, you are looking at the gap between this value here, which is X bar 115.52 minus the 115 that has been given to you here, divided by the same information, which is 1.6667. We are finding a new Z there. But watch it. Why are we finding a new Z? Because he's asking us for the probability. Probability. So we are finding a new Z there. What will be the value for this Z? Because once you know this Z, you can find the probability that they're asking for. You should get approximately 0.12 if you check. 0.12. Okay. So you check, that will give you 0.12. So we're going to go to the table and read 0.1 under 2. Hey, did you confirm that you have 0.12? This is it. You get 0.12. So let's go to the table and read 0.1 under 2. Let's not use this one. Let's consistently use this. 0.1 under 2. And like I said, you cannot even use the... If you use this one, you have to subtract, okay, from 1. So 0.1 under 2, that's it. What value is that? 0.1 under 2 is 0.5478. So you subtract that from 1. What do you get? By the way, the value is this. That's it. That's what you get. 0.1 under 2. 0.5478. So 1 minus that is what?
0.4522.
0.4522.
So that is a value that you get. That is a probability. Let's go back to the question. It says, what is the probability that a new system? So you get this one, and you read it from the table, you get this. Is that the same thing you had? Did you get 0.0478?
No, please. We got 0.4522. I think we subtracted from 1 instead of subtracting a half from it.
No, you subtracted from 1. You use the Z. I think because of the Z table I used.
Yeah.
So that's why I say that it's always nice to use the one that is 0.5 maximum. So this one, let me show you. So let's do it here. Okay. 0.12. That will give you 0.0478. So that gives you the answer even straight on. Because remember, if you check the value we are calculating, the value is positive. It's on the right of the 115. Do you see that? I didn't draw this, but look, if you had to draw, you had this, you had 115 here in the middle, and then we're looking at 115.2, 115.52 or something. So the value here is what you're looking for. The space is what you're looking for, and that is direct movement. That is direct movement. So whatever you get, you don't subtract, you don't do anything. And when you use that table of 0.12, you get this one straight away, 0.0478. And that is exactly what you get here. 0.047 points. I just hope you understand. If you don't understand, you will ask a question. All right. Then you add that one to the existing 0.5. Okay, you guys got the answer straight away, right? I think you guys got the answer straight away.
Yeah,
Use the other table.
Yeah.
Okay, good. You got the answer straight away, so it's still good. But here you have to subtract it from 0.5. And then that will give you 0.4522. So what it means is that there's about 45.22 chance that the new design will not be implemented, even though the true mean breaking distance is actually 115. Okay, so let's look at the general case. Okay, we finish all the examples. The general point is that you can have a situation where the standard deviation is known. It's known here. And then you can have another situation where the standard deviation is unknown. It's unknown here. But watch it. The one that is unknown, the sample size is large. The sample size is large. Unknown. Unknown means that it's like we are going into T, but the sample size is large. So we use Z. Then, and this is the formula for that. And then you have the final one, which is the standard deviation is unknown, but the sample size is not large, it's small. It's small here. So these are the three different cases that you can get the question on. Let's take one of them. Hypothesis testing. This is just one sample. One sample hypothesis testing. The drying time for a test specimen is normally distributed. So that means that we are dealing with a standard deviation of 9. The hypothesis is a one tail, as you can see here. And they are to be tested using a random sample of 25 observations. Very, very simple. How many standard deviation of the X below the null is 72.3? Remember, the mean is what? 75. So if you want the standard deviation away from the, if you have to draw this thing, this is how it will become. In fact, it is just going to be this. 75 is in the middle. You are looking for 72. Okay. 72 is going to be leftward. Okay. So the question is how many standard deviations are away from that 72? It's so simple. It's so simple. You can just look at it. What will be the value? How many standard deviations are below? Huh? It's very, very simple. First of all, we know that this is a two-tail. That one we know, so we don't have to. You just take the gap. You don't want to just minus, that's the gap. Okay. So we have the sigma. You're talking a lot like that.
Are you Betty? Check your phone.
Hey, Albert. This guy is not serious. So you compute a sample standard deviation because this is a sample situation. N is less than 25. So you calculate that. This is for the the sigma. Okay, population. So if you want for the sample, you divide it by the square root of that. That will give you 1.8. So 1.8. Okay. Now you are going to now compute how many standard deviation this 72 is below the 75, which is the mean that has been given. So you substitute it into the equation. Whatever you get, that question of how many standard deviations are away is the Z value, basically. So you substitute the 72 here minus the mean of 75 divided by the 1.8 standard error. That will give you a value of 1.55. It's negative because the 72 is below the 75, which is the mean. And so the whole thing is 1.55 standard deviation away from the mean. So the sampling mean of 72.3 is 1.55 standard deviation below the null value of 75. Any question on that? So when you hear how many standard deviation are we, it's talking about the z-value. All right. Now, the next part of the question, let's go back to the next part of it. It says that if x is 72, what is the conclusion? So I simply find now that we know the z-value, find the alpha. Okay, what is the conclusion using alpha? Alpha of 1%. So what will be your conclusion? So we have the null and alternative hypothesis. Okay. The null is that you have mu 75 and above. The alternative is this. So you find this one, you got a value of z. So you have to formulate a hypothesis, 75 against 75. One is below, one is above and equal to. What is your alpha? Alpha has been given to you as 1%. You see, you're moving from a z value into an actual hypothesis testing. So we need to find a critical value. Okay. So you have the z value of 1.55. If, in fact, in this case, you've been given a 1%, so its confidence level is going to be 99%. So you take that 99% and on the z table, you look for the 99% and you find the corresponding critical value. So you go to the 10, go and find the corresponding critical value for 99%. In fact, you can do that. I've put it there, but you can always find it here. So watch it, 99%. Remember, it's not 99.999, it is 0.99. It's exactly 0.99. Check it carefully, 0.99. You see between this and that, it's one of them. Okay, one of them is what you're looking for. So is it going to be 0.9901 or 0.9898? Which one? Which one is closer to 0.99?
No, 0.01.
Exactly. So it's the 011. So your corresponding z is going to be 2.33. And you're going to match that against the one that you found. So that's going to be 2.33. Because this one is on the negative side, it will also be negative. Okay. So the question now is, you got to make a decision, okay, between these two. Because remember, the actual z statistic is this. This is a critical value. This one we just found is a critical value. Again, when you draw it, let me draw it and show you. When you draw it, okay, this is the 0, and the critical value that we just found is this, negative 2.33. Where do you think this value will be? Will it be to the right or to the left? Obviously to the left, so that will be here. So it will be in the rejection region. Negative 1.55 will be in the rejection region. Okay, and therefore, you can now make your conclusion. Decision time. You reject if the z is below, and ours is below. Okay, ours, oh, is it below?
Yeah, because if you're moving from 1.55 will come before.
Then I shifted it.
The
Yeah, it
negative.
should be
Okay,
before.
let's ignore the negative and use the positive because it's
closest to
symmetric.
0.
Let's use, yes, go ahead.
Please, negative 1.55 is greater than negative 2.83.
And you saw me do that and you didn't mention it. Okay. Now that you have seen this thing, we all seen it the same time. So this is negative 2.33. So the negative 1.55 will be here. Okay, it will be inside it. So in fact, on the basis of that, you can now conclude that the thing is in the region of acceptance.
Yeah.
So we accept the null hypothesis at this stage. So at 1% significant level, you can conclude that that 72 is below, truly below, sorry, is it below? That 72
Okay.
Yeah. Okay, so we said that the 72 doesn't provide enough evidence to conclude that the true mean drying time is less than 75. In other words, the 72 is below the 75. Okay, is below the 75, which means that we accept the null or we don't reject the null hypothesis. And therefore, we do not reject the null hypothesis, and therefore we reject the alternative hypothesis. If you don't understand, ask. So that is the first part to this. Okay. The next part is, what is the alpha for the test procedure that rejected the null? Ask. So we are given a different value. What is the alpha? We simply want the alpha. In other words, yes, Emily.
Okay, Doc, please, I want a little clarity on this before we move on. When we say the critical value and then the test statistics, in this case that we are looking at, which ones are those?
In terms of Z, this is a mean. The critical value is the value that you either find using, one second, is a value you either find using the sample size and then the level of, or sample size and degrees of freedom, and then the level of alpha. So in this very example, let me just go back to it. In this very example, the critical value is the 2.233. 2.33. So that 2.33 is this. 2.33 negative, because it's on the left side.
Okay.
Of course, so when you go to the right side, it will still be, the same thing. Yeah, but that's it. Now, the test statistic, in this case, Z statistic, is it's not the critical value, it is the Z statistic. It's a test statistic. And this test statistic is negative 1.55. And negative 1.55 will be somewhere here. Okay, let's say it's negative 1.55. Now, the critical value, anything on the far left of the critical value and on the far right of the critical value is in the rejection region. So all of these are in the rejection region. So any value that falls there, but our negative 1.55 didn't fall there. If you check carefully, our negative 1.55 is within the acceptance region here.
Yes.
So that means that we accept the null hypothesis. Now, that will mean that you need to know what the null hypothesis is. Okay, you need to know what the null hypothesis is for you to accept it. Now, let's go back here. We were given a significance level of 1%. The null hypothesis, they say that, okay, if X is equal to 72, no, the null hypothesis was given to us here already. Okay, so we look at the null hypothesis. The null hypothesis says the drying time for a test specimen is the drying time. The drying time is 75 or more. And the alternative would be that the drying time is less than 75. Now, what we just did, it was in acceptance region. So we accepted the drying time. So it means that the drying time is above 75 or more. Actually, please just hold on. Let me continue. So we accepted the null hypothesis, and then we move on to the alternative. I don't know, what was the question you were asking?
But I think it's been answered. I was
Okay,
asking
yeah.
about the critical value and then.
All right, okay. So that explains the critical value in the test statistic. Now, the next part of the question says, what is the alpha? Let me clean this. What is the alpha for this test procedure? Now, we know that this is a left tail test, okay, but we've been given an alpha value of, we want an alpha value when the z value is 2 point that. Anytime you have been given a z value, to get a corresponding alpha, you dump it into the table and find it. So go into the table. In fact, you guys have the table. Go into the table and find 2.88. But I don't have to always find code. What do you get? Depending on whichever table you are dealing with, it's a straight movement. This one is a straight movement. What is the alpha value? You go and read 2.8 under 8. They want me to show them.
0.0019.
00 what?
0.0019.
No. No. Or did you round up?
Doc, I got 0.002.
Exactly, that should be it. That should be it. Director, do you know why she got that answer?
Yeah, no, she approximated it to.
Okay. Oh, approximated. Are you sure you approximated, Emily?
No, Doc.
There's
That's
no
what the calculator
approximation.
gave me.
You also said calculator.
Yes, I used calculator. So I checked the 2.88 on the full
Exactly.
table.
You get this one.
Yeah, you get 0.9980. So 1 minus that is what I got.
Okay.
The table is what gives you the answer. That's for the calculator. There's just the table is the main one.
Okay. No.
All right. So that is a real thing you should do. All right. So that should give you 00220 or 002. That's the answer that you should get if you have to write this. In fact, it's asking you for the alpha, and that's it. Once I have the z, I can always find alpha, and this is it. Now, the very last one, and then we're done for today. The amount of shaft wear after a fixed mileage was determined for each of the 8 internal combustion engines having a copper lead as a bearing material, resulting in X value of 3.72 and a standard deviation of that. Now, that sentence of resulting in X value, he has not given you the mean. Okay, that is not part of the mean. He says it resulting in X value. He didn't say resulting in a mean of. What he's giving is a sample. A sample. Now, assuming that the distribution of shaft wear is normal, now you know it's normally distributed with a mean mu. Use the t-test, at level 5% to test the following now. So now he's giving you the mean itself. This is so easy, so you don't need to bother yourself. How do you find that? It says that assuming blah, 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 use the t-test and test this hypothesis. What is our hypothesis? The hypothesis here is that mu is 3.5. What is mu? That is amount of shaft wear after a fixed mileage. Okay. That is equal to 3.5. And then the hypothesis is that it's greater than 3.5. Or basically, it's not equal to, but it's not equal to, it takes the one angle of it's not equal to, which is greater than 3.5. So how do you test whether this is true or not? You just substitute it into the t. Now remember, the t is going to be x minus mu over the standard error. What is the standard error here? the standard error is going to be S over the square root of N, the same thing.
Yes.
So you substitute that value. Our X has been given to us as 3.72 minus the mean. The mean was given down there in the question A as 3.5 divided by S is 1.25 over the square root of N, which is 8.
8.
So you find the T statistic. And then when you're done, you juxtapose that with a critical value. So what is a T statistic here? So this is T statistic. So that means that you got to use the T table. Let me quickly find the T table for you. It looks like, did I give you the T table? I just hope I did. I just hope I did give you the T table. But what about this?
Doc, please, yes, we have it.
Perfect. So you're going to use the T table to make your judgment. But first, find this is T statistic. What's the value?
0 point.
Yeah, sure. Yeah, 0 point. Correct it to the nearest whole number.
0.5.
Perfect. So that is a 0.5. I hope you should all get it. It's 4.999 something. All right. So that is a T statistic. Let me call it T statistic. It's 0.5. Now, how about the T critical value? Now, unlike the Z1, okay, the T, the critical value is giving us T subscript alpha N minus 1. That's how you get a critical value. Okay. In other words, we are dealing with T subscript alpha. What was the alpha value given to us here?
0.05.
What was the N?
N is 8.
So N minus 1 is what? 7. So we go to the T table, look at this section here, okay? And then you ask yourself whether we are dealing with a one tail or two tail. Whether we are dealing with a one tail or a two tail. And remember, we always use alternative. And looking at this alternative question, are we dealing with a one tail or two tail?
Doc, one tail.
One tail. Okay, so you pick on one tail, and then you pick on 0.05 under the one tail, which is this. You match that against 7, which is that.
Okay.
Your value is what? 1.895. So your T critical value is 1.895. And our T statistic was 0.5. Now, to reject the null hypothesis, your T statistic must be greater than the critical value. Okay. Reject null if T statistic is greater than or equal to the critical value. So in our case, should we reject or we don't reject?
You shouldn't reject.
You shouldn't reject. That's true. Okay. You know what that means? If you are not rejecting, it simply means that there's not enough evidence, at this 5% to conclude that the mean shaft wear exceeds that 3.5. Let me show the way you should work it. Sorry, where are we? Okay, so this is all that we've done here. The mean is that you find a 0.5, you go and read the 8 minus 1 degrees of freedom, you find 1.86 for the critical value, and this becomes your conclusion.
So,
yeah.
Please, reading from the table, if you mistakenly read from the two tail instead of one tail, is there going to be any difference?
Yeah, there will. Let's check. Your answer was right there in your face. So if you take this one, it's still going to be at the 7 instead of 0.5. If you go and take 0.5 one tail, and you rather go and take 0.5 two tail, you will not get this. Okay. You will get that. The conclusion will be the same, but you have made a numerical error.
Okay. Yes, please.
The conclusion will not change, but you made a numerical error. So don't make a numerical error.
Yes, please. Yes, please.
Correct.
Thank you.
Now, the next part of the question. Okay. Where's it? Let's go back here. It says that when the sigma is rather 1.25, remember, you see here, it told you that the sample size, the sample standard deviation is 1.25. But now he's not telling you about the sample. Which one is he giving you here?
The population.
The population. Now he's telling you that it is 1.25. That is known. He's even supporting it more. It is known. In this case, you don't have to use the T. You have to use the what?
Is it a Z?
Correct. It's known. It's known. Okay. Now the question is, what test would you use? See the question. What test would you use? And find its type 2 error probability, of the test for the alternative mu being 4. So first of all, we know that whatever we are going to use what? A z-test, because the sigma is known. Okay. Now, remember that the null hypothesis wouldn't change. And he has given us a new mu. Do you realize that? Do you realize he's given us a new mu?
Yes, that's the
previous
4.
Exactly. The previous one was what? 3.5. And now he has given us 4. So if we are to rewrite the hypothesis, you're going to write the hypothesis with that 3 point, with that 4. Okay. Now, normally with the Z, you need to now use the 4 to do the calculation, but you don't have to do it because alpha has been given. Remember, Z is the highest level of T. Z is the highest level of T. So with the alpha still being 0.05 and it is still one tail, you can find a corresponding Z straight away. Because if alpha is 5%, it means that how many percent confidence interval?
0.95.
Yeah. So you can go to the Z table and find that. Let's go to the Z table and find the 0.5 correspondence. Where's my Z table? I hope it's this one. Okay. So we are looking for 0.5 per. Sorry, you're going to 0.05. 0.05. But this one gives us what? This one gives us what you are seeing here gives us probabilities. Okay. So we need to now, we are dealing with 0.05. So you need to take the reciprocal. 0.05 will be 0.9 what? 99. I mean, confidence interval for that will be what? 0.995. 0.995, isn't it?
Yes.
0.995. So we are rather looking for 0.995. 0.9999. This is 993. This is 996.
Yeah, it's going to be between 2.57 and 8.
What is that?
So 2.57
Oh,
will give you
sorry. I'm using the wrong table. Okay. We are supposed to use the Z table. The T table. The T table.
Doc, please, the standard deviation was known. So you said we were rather going to use the Z table.
Yes. No.
Hold on, let me check.
The Z test.
You said the standard deviation was what?
Known.
Okay, wait. Okay. Okay, let me use our usual Z table. This one.
So in other setting, which of the tables are you going to give? Is it this one?
It's all of them.
Okay.
All of them. Or I should give you. I can give you this one alone. I just want to take care of everything. But when you have all of them, people have choices. Okay, so we are looking for 0.05%. So 5%, you got to match it here. You see this one? This is it. You have to subtract it from 0.5. That's all I'm trying to say here. If you subtract it from 0.5, you're going to get one of these. And if you don't take care, you think that, okay, which one will you take? Which corresponding Z will you take?
I'll take.
Be careful. Be careful. Come on, I don't want to say.
Is it right?
No, they seem the same. Like
So
they are all 0.5, 0.5.
So which one will you take?
Okay, so Doc, I would have taken the 4505.
No, you take both.
Hello, Doc.
You take both. So you're going to take 1.64 and then 5. Do you get it?
Okay.
Because they are all going to be closest to 0.5, isn't it?
Okay.
Yes.
Yeah, so you take both of them. So you take 1.645, which takes both this one and that one.
Okay.
That's it. So your corresponding Z value for this 5%, in fact, just for so you know, 5% will always give you this value, 1.645. Always for Z. Okay. So now that you've gotten that 1.645, what do you now do? Let's go back to the question. Okay. We got to now substitute it into our results. Okay. So we are going to rewrite the entire formula for the Z and substitute the 1.645, whatever the Z is. So you write the Z formula is Z equals to X minus mu over
The standard deviation.
Standard deviation. What's the other one? Over the square root of n.
Yes.
Okay. What is the n?
N equals 8.
Okay. You see, n equals 8, but that is not what you were specifically told that n is what? You were specifically told that n is 8, but you were specifically told that we are dealing with unknown standard deviation. So that's what you're using. You see, because n is 8, somebody might still be tempted. But he didn't focus on n. Look at the question. His focus was on the population standard deviation is known. So that is what makes you use the Z. So you are still going to put the n there. Instead of the n, I wrote 8. Okay, so now let's substitute. We know the value of Z now, don't we?
Yes.
We know.
Remember what the question was asking you. The question says that when the population standard deviation is known, what test will you use to find its type 2 error probability of the test for the alternative mu? Okay, so first we need to know the test. We know the test. That's what we are using. But you're not just knowing the test, but you are also finding the probability value. So we have to find this test before we go and use it to calculate the probability, match it against the 4 that he has given us. Okay, so we know that we have our 1.645. So we are substituting that to get the value of the X because we don't know the critical value. at this stage, we don't know this X. We don't know this X value. That's what we are finding. So to get this S value, we know the Z value here. The Z value is what? 1.645. Okay, equal to X bar minus mu. Okay. Now we take the original one because that's what we are dealing with. The original one first, which was what? 3.5. Okay, divided by sigma, which is 1.25, divided by the square root of 8. So you find this value. You find the X value for this first. And if you go do the manipulation and everything, you should get X value to be, you cross multiply this by that. The square root of 8 is what? 0.4? 0.442, I think. Yes. Find this value and let me see.
Will you get? I had negative 7 points.
Huh?
No.
I mean, you go ahead.
Okay, so mine was 4.23.
Perfect. It should be 4.227. Let's make it up.
Okay.
So if you work it well, you should get 4.
I mean, please, have you multiplied by the 1.645 already?
Yes.
Okay. I thought we were evaluating the.
We are finding the X bar
Okay.
or the X value. Okay, so what is our X bar now? Our X bar now is this. Now remember, we don't know. You see, he has changed the standard, what do you call it? He has changed the sigma. He says sigma is 1.2, is known, and we don't know the X value. So that's what we are finding first using the previous analysis. Then, now that you got the X value, we now go to the question that what test will you use to now calculate? But here's the clue. To find the type 2, it's type 2 error probability, if the alternative is now changed to that. So the mu has now been changed to what? That is a new prime. It's a new prime because the previous mu was mu. But the new mu, that's why it's called it new prime. So how do you find the new Z and the new probability test, given the fact that this time sigma is known? So we rewrite the formula because right now we know the value of X bar. Okay, so you rewrite the formula using the same formula. We know the value of X bar now to be this. So now let's find the Z value using the same 4.227 minus the new mu. What's the new mu?
4.
So you now substitute that same 4. Okay, divided by the new standard deviation. Of course, that one was given because you not the new standard deviation, the new standard error, because you calculated that using the new population standard deviation. So find the new mu for us, divided by 1.25 over this 8. I think this one gave us 0.422 or something. So now what is the Z critical? Sorry, what's the Z statistic? If you check the nature of this question, it's loaded. It's like, I don't know, but I know. I don't know the X bar. Find it for me, given the fact that the only thing I've changed here is the sigma. Now that I've changed the sigma, find me the new X bar using the old story. But after you've gotten that, I'm now giving you a new population mean. So use that new population mean to tell me whether I got to reject the null alternative hypothesis. What was your new B? New Z.
Okay, Doc, so the new Z is 0.514.
Good. Okay, or 4.0.5136. That's
Yes.
correct. So now that you have that value, remember that B here is type 2 probability. Are you aware? It's the probability of
Yes.
committing a type 2
Because,
error.
yeah.
Good.
Yes.
So now the probability of committing a type 2 error given the mean of 4, what would that be? Okay. In other words, you are finding the probability of Z equals to 0.514 that you just mentioned. The probability of Z equals to 0.51. Remember, it's not actually equals to, it's going to be less than. Why? Because when you look at the formula carefully, if you check this value, if you check that new 4 here, it is actually less than the new Z that we have found. Sorry. I mean, if you check the new Z that we have found, we got 0.5 something. The new Z is what? 0.5?
0.5136.
Yeah. 0.51, let's say 4. Okay. This one is less than the mean. So what we are looking for is we are looking for the probability that Z is less than or equal to this value, 0.514. We are looking for p-value for it.
Okay.
That's the type 2 error that is asking for. So you go and read this one again on the table to find the probability. Remember, this is a Z value, which you always read. I've always told you that anytime you have the X, you can use the X to find the Z. You can use the Z to find the P. So that's what you get. So when you go and read this one on the table, what do you get? 0.51 / 4. Okay, let's check. Let me go to 0.51. Is it 0.51 or 0.5/1? It's 0.5/1, right?
Yes. So 0.1950.
50.
Yeah, what is that? Then I mean,
Look, yeah, where the is.
yeah. Good.
Yes.
0.1950. Okay. But if you check this is a positive value we are finding, not a negative value. Okay. And we are looking for, if you check the formula I've just written, we are looking for the space below that number. Oh. Okay. Remember, I wrote probability of Z less or equal to 0.51. If I were to draw, you have this value of 0, and then the plus here is 0.51. Okay, that's a Z. All of them are Z values. And then we are looking for the space below all of that number. So now that you've gotten this number, okay, the probability value, you add it to what?
0.5.
You add it to 0.5, and that will give you the type 2 error probability.
Okay.
Add it to 0.5, and that will give you type 2 error probability. I mean, if you follow the trajectory, and I'll show you the trajectory if you still didn't get it. Tell me the answer first.
0. Wait.
0.695.
That is the percentage. Okay, so it says what test would you use, and then after that find the probability of the test. Okay, find its type 2 probability. Okay, for this particular alternative procedure that we get to. So let's quickly go through that.
Okay.
So this is a new known 125. The old hypothesis is there. The alternative value for the type 2 error will be 4. It was given to
Doc,
us.
please, we are still seeing the table.
Oh, sorry. Let me start. This was a known, as for the first one, you understand. So you're looking at the second one. The first one we did that, we got this. Because that one was when the T was unknown, okay, and then we had to use the T value. The second one here, the sigma is known. And so we know that we got to use the Z value. But we are told, and that this is the original hypothesis. From this original hypothesis, we are told that alternative value of the type 2 error has been given to us with a mu of 4. Okay. Since the Z is known, we have to use the Z test. The sigma is known, we have to use the Z test. Now, what are you using the Z test for? Normally, you use the Z test when you know the value of X, isn't it? But there was no value of X given. Check it. We don't have the value of X. So that is why we have to now go to the alpha that was given to us. And the alpha was 5%. We find that 5% is a probability value. We find the corresponding Z value here. That gives us 1.645. We use that Z value here to find our X bar. Okay. So now we can now convert it to the X bar, which gave us what? 4.227 or 4.23. Now that we have the value of the X bar, we are looking to reject the null hypothesis if the X bar is greater than this one that we have, the critical X bar. Now, we have to compute the type 2 probability when the mean has already been given. Type 2 probability is given by this, but we are using type 2 probability with its new mean, which is 4. Type 2 probability is given by X less than or equal to 4.22. Now, why? Because it comes from the formula that we were originally given from here. Okay, we're looking for, first of all, we said that anytime we get an X bar bigger than 4.22, we're rejecting the null hypothesis. We are looking for the type 2 probability that will help us not reject that null hypothesis. Under the true mean of this, we can, and then of course with the standard deviation of 4.422, this is the square root of the 8 that we had. We standardize the variable. Using this one, we can find the new Z. Remember, we use a Z to get an X, but now we are using the X now that we found to get a new Z, because now a new mean has been given to us, and that gives us this. So we have 0.514, and this, when you read from the table, okay, from the Z table, you're going to get, if you read it from the 1, the probability that is up to 1, you'll get this. But you see, that's why I keep saying that sometimes one of you said that, oh, which one are you giving to us? And inside the person has made a conclusion that he wants this. If you go to this one, okay, and you go and find 0.5, it was 0.5 what? 16 or 513.
Yes.
51.
0.51. Yeah, 0.51.
Okay, so this is 0.51. You see, it gives you the answer straight away.
Yes.
And yeah. So that's what I'm saying, that you got to know which one angle you are looking at. But you just have to know whether you're subtracting or you're adding. That is a clue. And here, we are adding if we are using the 0.5 table. But if we are using the 1 table, you don't need to do the addition. So that gives you this final answer. So there is a doubt. There's about almost 70% chance that the test fails to detect a true mean of 4. Now, that way the test fails to detect a true mean of 4 is a type 2 probability. The probability of committing a type 2 error. That is if you accept a false null hypothesis, that's what happens. So that is how you handle these calculations and all of that that you'll be doing. Emily, your hand is still up.
Yes, Doc. Doc, please, before you come to this, I know previously that Z was calculated as the mean minus, sorry, the X minus the mean over standard deviation. That's what I've been using so far. But with this one, I saw the standard deviation divided by the sample. So I just want to be certain of the
What's the
condition
difference?
under which this.
Okay, you use this one only when you are dealing with hypothesis.
Okay, so
This
for
one you
all
see,
hypothesis, this is the
exactly, for
formula.
all hypothesis, you are using this. But when you are not
Okay.
looking at hypothesis, you see, hypothesis is where you have a null, you have an alternative hypothesis, you need a critical value, and then you need a test statistic. You juxtapose the test statistic. Let me use Z rather. You juxtapose the test statistic against the Z critical. And then finally, you compare the p-value with the alpha. Either as long as it involves hypothesis testing, this is the formula. But if you are just looking for the probability values without hypothesizing, without sample size and sample standard deviation, those things being given. Remember that where we use the usual probability, the one you are talking about probability,
Yes.
there was no hypothesis there.
Yes.
And that is why we define Z to be X. That one was not even X bar. It's X minus mu over sigma.
Yes.
That is for standardization. This one, you're not using it for hypothesis testing.
Okay, thank you.
Okay. So guys, in terms of the exams, there's going to be 6 questions you answer for, basically. 6 questions you answer for. There will not be a question where it cut across and it's going to confuse you. So if you are going to answer a question on hypothesis, you're going to answer a question on hypothesis, as you see here. If you're going to answer a question on probability, different kinds of probability, we've done hypergeometric probability, negative binomial probability, Poisson, normal, and so forth. You are going to learn them. The first one we looked at, what was the first one we looked at? Well, let me just stop here.